In this video, I'm going to go through some worked example answers to past paper questions for Combined Science Physics Paper 1, focusing on radiation topic higher tier questions. So let's start with question 1. So it tells us that some people used to think radioactive substances had health benefits. And in the 1920s, a water container called a revigator was sold. There's a picture on the bottom right. And it was the walls of that container that had radioactive isotopes in them. So the water was put into that container overnight, and then people would drink the water the next day. So we can see from A, the water was irradiated and contaminated. So we're going to be asked about the difference between those two things. We've got to explain how irradiating and contaminating the water affected the hazard. So if I'm affecting the hazard, I'm either increasing it or I'm decreasing it. So I need to say whether irradiation increases or decreases the hazard and why, and does contaminating the water increase or decrease the hazard and why. That why gives me the explain part of my answer. Now there's 4 marks. I'm already directed to look for irradiation and contamination, so let's put 2 bullet points down for each, and then I need to fill in the information. So starting with irradiation, the radiation will pass through the water and the water doesn't become radioactive. So that's the key thing about irradiation. You're not making anything radioactive, you're passing radiation through. Now that radiation can kill pathogens. Which is obviously going to reduce the hazard associated with the water. So I've said how it affects it, it reduces the hazard, and why, as it passes through, it kills pathogens. Now looking at contamination. So contamination means that the radiation enters the water. So the isotopes enter the water. And therefore, the human body, when the water is drunk, so obviously we've increased the hazard because we've got radioactive isotopes inside the body. So there's our 4 marks. And I can just double check. I've talked about irradiation and contamination and what's happened to the hazard and why. Part B, we're told here that the water contains radon-222 and vanadium-52. We're interested in the vanadium as a beta emitter. We've got to identify the correct nuclear equation, ticking only one box. Again, check the instructions. So even if we're not sure about what happens in beta emission, remember the numbers on the left must equal the numbers on the right. So if I have a look at the first one, I've got 52 is my mass, take away 0 does give me 52, that looks okay. But 23 take away -1 doesn't equal 22. 23 take away -1 will give me 24. It's definitely not the first one. Looking at the second one down, I've got 52 take away 0 gives me 52. That's looking okay. 23 take away -1 does give me 24. So this is looking okay so far. Let's check the other ones. Next one down. This time I've got my vanadium splitting into 2 products. let's have a look at these numbers first. So 52 is the same as 52 plus 0. Yes, it is. And 23, is that the same as 22 plus negative 1? Well, it isn't, because 22 plus negative 1 will give me 21. So we know it's definitely not that one. Let's have a look at the one at the bottom. So 52 becomes 52 plus 0. That works. 23 becomes 21 plus negative 1. That would work as well. So on the surface of it, I've got two nuclear equations that look like they would work. How do I work out which is the correct one? Well, in my first one, I've got my vanadium. I'm taking away the beta particle to make chromium. In my fourth one, I've got vanadium splitting into chromium and a beta particle. Now, this is the correct version because we're always representing that original particle. I just started with a vanadium particle and it's split into chromium plus beta. So our correct answer is the bottom one. But it's quite a sneaky question, that one. Okay, part C. The table below shows the half-lives of the radon and the vanadium. That's 3.8 days and 3.7 minutes. Obviously note the big difference there. We're told that the scientist measures the radiation emitted by each of those samples and then repeats the measurements 7.4 minutes later, to be very precise. We need to explain how the activity changed after 7.4 minutes. And we need to do that for each of radon 222 and vanadium 52. So if we look at our answer, we know we've got 4 marks and we've been directed to talk about each of the 2 isotopes. So that gives me 2 points to make about each isotope. So first of all, I'm going to look at those half-lives and compare it to that 7.4 minutes. So with radon 222, obviously the half-life is much higher than the 7.4 minutes. So that means that although the activity will have decreased, it will have decreased by a tiny, tiny amount because we haven't had much time go by compared to the length of the half-life. So the activity decreased by a small amount. It's fine actually to say it will have hardly changed at all. Looking at vanadium 52 then, if we look at its half-life, it's 3.7 minutes, which is less than 7.4 minutes, and if you spotted it, it's actually half of 7.4 minutes. So for vanadium 52, the half-life is half of 7.4 minutes. So 2 half-lives have passed. So the activity has halved twice as well. So I can say it's going to be a quarter or 25% of the original. So it's going to decrease a lot. Now I think in the mark scheme it allows you just to say that it decreases a lot, but obviously it's nice to put that little bit of extra detail in that it will decrease to 25% of original. Okay, part D then is asking us, scientists who monitor the effect of drinking water, have their methods and results checked by other scientists. What name is given to that process? So we just need to know that that is peer review. So just make sure you remember that phrase. Question 2. So a smoke detector contains a source of alpha radiation in a plastic case. A source of beta radiation would be more hazardous than alpha. Explain why. So I've got 2 marks for my question, so I'm going to give myself 2 bullet points. And I need to think about why beta is more hazardous than alpha. So what's a property of beta that makes it more hazardous? And I'm going to use the plastic case as a bit of a hint here. So beta is more penetrating. And that means that it can get through the plastic case. Which obviously alpha can't. Now, because of that, it could irradiate people in the building or the home, depending where the smoke alarm is. So that's why it makes it more hazardous. Another possible answer is that beta has a greater range than alpha, so therefore it's more likely to radiate people as well. So you can have either of those. I think the one about it being more penetrating is better because we can talk about the importance of the plastic case. Part B, we're talking about actinium, which is a source of alpha, and we're saying here that it emits alpha and turns into francium. We've got our equation there, and we need to determine the values of A and Z. Remember, determine means to calculate or work out without necessarily using an equation. So again, I always recommend that we add in the missing information about the alpha particle. So we know alpha has a mass of 4 and it has an atomic number of 2 because it's 2 protons and 2 neutrons. And I'm trying to work out those missing numbers A and Z. And remember, the numbers on the left-hand side of the equation must equal the numbers on the right-hand side. So on this side, on the right-hand side, I've got 223 is the mass, plus 4, there's the plus sign there. So 223 plus 4 would equal 227. So on this side of the equation, A must equal 227. And I can show my working here actually as well. And then if I look at the atomic numbers on this side, I've got 87 plus 2. So 87 plus 2 equals 89. So Z must be 89. Part C of this question then. A teacher wants to find out what nuclear radiation is emitted from a source, an unknown source. The teacher places different barriers between the source and detector and records the count for 30 seconds after the barrier is in place, and then the table below shows the results. So we've got nothing, paper, aluminium and lead. So we know that alpha is stopped by paper, beta will be stopped by aluminium and gamma will be stopped by lead. So that's the information we're looking for in that table. And each time we're going to compare what's happening to what happens when there's no barrier. So that's the source just being detected without anything in the way. So we know that with no barrier, the source produces 985 counts in 30 seconds. So we can see that when we put the paper in, it does go down. We can see that when we put the aluminium in, it decreases again. But we're getting nothing going past the aluminium or past the lead. We've got 4 marks. So again, we want 4 bullet points. And now we're going to look at the information in the table and then turn that into an answer. So what we see is that when we put the paper in, the count goes down. We know that therefore there must be alpha radiation because otherwise, if there was no alpha radiation, the count wouldn't change. So first thing we say is the count decreases when a paper barrier is added. So that's the fact we're taking from the table, Therefore, the source emits alpha radiation. Now, as you can see, there's 4 marks, so we haven't finished. Let's look at the rest of the information. So now when we add aluminium, the count goes down again. So some radiation clearly made it through the paper, which could be beta or gamma, but didn't make it through the aluminium. Now we know gamma would go all the way through, so that means there must also be beta radiation. So the count decreases with aluminium. So beta radiation is also present. And I think the most common mistake I see in a question like this is that students get the first bit right about alpha because they see the effect of the paper and forget that with 4 points there must be something else going on. So it's a really good higher tier question. Part D, the graph shows the activity of 4 different radioisotopes A, B, C and D, so it's showing how that activity changes over time. So this is a decay graph, if you like. We've got to write the isotopes A, B, C, D in increasing order of stability. Then we've got to explain our choice. So the first thing we need to understand is that something with a very long half-life is more stable because it takes longer for the sample to break down. Something with a really short half-life is not very stable at all because it will break down completely very, very, very quickly. So what we're looking at is the things with the shortest half-lives are going to be the ones which are the least stable. So I'm actually going to start with the explanation first because it's going to help me answer the question and put them in the right order. So I really need to have sort of 2 points in here somewhere. So the first thing is that more stable isotopes have longer half-lives. So the order is in increasing half-life. So there's the 2 parts of the explanation. Now I need to work out which one is which. And at least now, if I interpret the graph incorrectly, I'm still getting the 2 explanation marks. So the one with the shortest half-life, the one that halves the quickest, is actually D. And if I look at D and how quickly it drops to half, we're just over 5 years, so it's quite short. The next one is going to be B. If I look at B and I look for where it halves, 250 to about 125, it's taking a bit longer, it's just over 10 years. If I look at A next, A halves, well in fact it's taken about 20 years to halve, and then if I look at C, which is the last one, it hasn't actually halved in 20 years, it's not even got anywhere near half, so that's the most stable one. Question 3. This is quite a nice question, it's just some knowledge bits here. Chernobyl disaster happened in 1986. Radioactive isotopes were released into the environment. That included alpha, beta and gamma radiation. And that first question just says, what is an alpha particle? So it's going to be 2 protons and 2 neutrons. Nice easy mark. Which statement about beta radiation is true? Again, make sure we only tick 1 box. So we just need to go through. It's the fastest moving type of radiation. That's not true. It's the type of radiation with a negative charge. Well, we know it's made of an electron, so that one would be true. It's the radiation with the greatest mass. Well, that's not true. That would be alpha. The greatest range in air, no, because we know that that's gamma. So having eliminated the other three, and we know that number 2 is correct, we can confidently put our tick in the second box. Question C, another knowledge one. Which statement about gamma radiation is true? Again, tick one box, but this is a sneaky one, so read it really carefully. So it starts off with, it is a low frequency electromagnetic wave. Now it's very tempting to say, oh yes, I know it's one of those, and assume that's the right answer. But it says here low frequency. Now gamma is right at the top end of the electromagnetic spectrum. It's very, very high frequency. So despite the temptation, I need to check that and realise it's wrong. It causes the charge of the nucleus to change. Well, that's wrong. Alpha and beta have an effect on the nucleus, but gamma radiation is just an emission of energy. It causes the mass of the nucleus to change. Well, that's wrong, because gamma radiation is an electromagnetic wave. It doesn't have any mass. It has a long range in air. Well, we know that's true because we discussed that in the last question. So it's actually the last one that's the right answer. So in some respects, a very easy question, but a sneaky one. So watch out for those. Part D. The table below shows the half-life of 2 of the radioactive isotopes that contaminated the environment. So we can see we've got cesium-137, 30 years, iodine-131, 8 days. A big difference, so you can kind of see where the question's going. A soil sample was taken from around Chernobyl in 1986. The soil sample was contaminated with equal amounts of that cesium isotope and the iodine. Explain, there's my command word, how the risk has changed between 1986 and 2018. Both isotopes emit the same type of radiation, so we can sort of put that to one side as a sort of control variable. Let's think about how we're going to organise the answer. 4 marks, 4 bullet points. And because we're looking at 2 different isotopes, that means 2 bullet points per isotope. So 2 for cesium and 2 to talk about iodine. I now just want to home in on this bit here. We can see that that is 32 years have passed. And if I write that down here, we can clearly see that cesium has had about 1 half-life pass, where for iodine it's many, many, many half-lives. So the first bullet point of each of these, I'm going to comment on how the half-life compares to the amount of time that's passed. So for cesium, we've had approximately 1 half-life has passed. Whereas for iodine, many half-lives have passed. And of course, we're talking about since 1986. So for the second bullet point in each, I now need to comment on how the risk has changed. So for cesium, the activity is half. So the risk has decreased, but it's still high. Whereas for the iodine, the activity is going to be really low, and the risk is also therefore going to be really low. So the activity, I mean, it's almost 0 at this point. So very low risk. So hopefully you can see how I structured that answer. Question E. So we're asked to determine, again we're going to do a kind of calculation, the year when the activity of the cesium will be 1/32, 1/32 of its original value. So we know that 1 half-life is 30 years. So what I need to know is how many half-lives are going to go by. So let's start off with, when we start, we've got 1 or 100%, if you like, of our activity. And then after each half-life, it will halve, then the activity will halve again. So I've got a quarter left. It will halve again. So I've got an eighth left. It will halve again. so I've got a 16th left, and it will halve again, so I've got a 1/32 left. So now it's going to be one half-life here, a second half-life to take us to a quarter, a third half-life to get to here, a fourth one here, and a fifth half-life there. 1, 2, 3, 4, 5. So that's 5 half-lives. Now you're going to get a mark for working that bit out. So we know that one half-life is 30 years, so 5 half-lives times 30 is going to give us 150 years. So that's how long it takes for the activity of the cesium to halve 5 times to get down to 1/32 of its original value. Again, you get a mark for calculating that bit. And then the third mark is working out from 1986. We've got to add 150 years, which will take us through to 2136. And there is your final answer, and that is your third mark. Question 4. Atoms of the isotope bismuth 212 decay by emitting either an alpha particle or a beta particle. The equation we've got there on the right hand side shows what happens when the atom of bismuth 212 decays by beta emission and turns into polonium 212. Bismuth and polonium have the same mass number. What is mass number of an atom? Nice question this, because it's the same in physics as it is in chemistry. So it's the number of protons and neutrons in the nucleus. Okay, part 2. Beta decay does not cause the mass number to change. Explain why not. So really we need to remember what's happening during beta decay. So if you remember, beta is an electron coming from the nucleus. There are no electrons in the nucleus. We know that, it's just protons and neutrons. So something changes in the nucleus to allow an electron to be emitted. So what happens is we have a neutron turns into a proton and electron. The electron is the beta particle. So there's my first mark for stating what happens. I could also say there, I lose a neutron and gain a proton. It's the same thing really. They don't mind which way you put it. Therefore, point 2 for the second mark, because a neutron and a proton have the same mass, there's no change in the mass number. So there's no change in mass number. There we go, second mark. Part B. So when an atom of bismuth 212 emits an alpha particle, remember it can emit an alpha or a beta, the atom decays into thallium. The alpha particle is the same as a helium nucleus, and there's the symbol representing it. And don't forget, for alpha particles, we can represent them as alpha or helium nucleus. It's the same thing, because 2 protons and 2 neutrons is a helium nucleus, which is the same as an alpha particle. Part 1 then, the equation below represents the alpha decay of the bismuth. Complete the equation by writing the correct number in the 2 boxes. So remember that the numbers on the left-hand side of the equation must equal the numbers on the right-hand side of the equation. So I've got 212 is my atomic mass on this side, must equal a number plus 4. So this has got to be 208, because 208 plus 4 equals 212. And then the same on the bottom, 83 has got to equal a number plus 2. This must be 81, because 81 plus 2 equals 83. Part 3, it's impossible for bismuth to produce the same element through alpha decay as it can through beta decay. And we're asked to explain why. And again, there's two parts to this answer. So the first thing to say is that the element is determined by the number of protons in the nucleus. So we know that from chemistry as well. The atomic number or proton number tells us which element we've got. So the element is determined by the number of protons. So that's the first point to make. The second point to make is that during alpha decay, we've seen here we lose 2 protons, but during beta decay, we gain a proton. So the number of protons available after decay is completely different. So we can just summarise that by saying we lose 2 protons in alpha decay, but gain 1 proton in beta decay. And so there's our answer. Question 5. Some small fractures do not show up on an X-ray image. To see the fracture, doctors inject the body with a radioactive isotope. The image is formed by detecting radiation as it leaves the body. The figure below shows the image of a foot after the patient was injected with the radioactive isotope technetium-99. You've got that on the bottom right there. Technetium-99 emits gamma radiation. What is gamma radiation? So a nice easy knowledge question, but it is higher tier. They're going to want a little bit more detail. So we can say it's electromagnetic radiation because we know that. Let's pop that in first. But to add that detail, emitted from a nucleus. So they just want you to put that bit about this idea it's nuclear radiation. That's a little bit of detail we want on that higher tier. Part B, we've got an explain question. Explain why a gamma emitter is used. We've got 2 marks here. So again, I need to make sure I include 2 points in my explanation. So the first thing is to think about what the property of gamma radiation is that makes it useful, and then why that is a useful property. So gamma radiation is very penetrating. That's the key idea. So lots of radiation will leave the body. And the second point, and can be detected. Outside the body. So we use something rather like an X-ray plate, and it's put outside the body and it detects the radiation as it leaves. Okay, last bit then. Technetium-99 has a half-life of 6 hours. Give the meaning of the term half-life. Again, we're just looking for a definition here. So it's the time taken for half the nuclei in a sample to decay. There's our definition. You can also say it's the time taken for the counts per second or the activity to halve. That would also be fine. D. After treatment, hospital equipment may become contaminated. Describe the level of hazard associated with that contamination with technetium-99. You should include in your answer a description of how the level of hazard changes over time. So it's telling us there exactly what we need to do. Don't get sidetracked by contamination. We don't need to explain what that is. We just need to describe how the level of hazard changes over time. We've got 3 marks, so we've got 3 bullet points. We're going to start off with the fact that the hazard level is initially high. Then the hazard drops rapidly or decreases rapidly because technetium 99 has a short half-life. Half-life's about 6 hours, which means that every 6 hours the activity halves, and within 24 hours you're down to a very, very low level of activity. That's why we use it in hospitals. Some of the hospital equipment may become irradiated, so we've now got irradiation as opposed to contamination, and we need to describe how equipment becomes irradiated. So we know contamination is about a radioisotope being on or in something or somebody. But when we're talking about irradiation, then the equipment is exposed, it's a good word there, it's exposed to ionizing radiation. So don't forget, all the way through this topic, we're talking about nuclear radiation because it comes from the nucleus of an atom, and we're talking about ionizing radiation. It changes the electron structure around an atom, and that's how it does damage. And then F, why is irradiated equipment not hazardous? Again, we're looking at that difference between contamination and irradiation, and the main reason is irradiated equipment does not become radioactive. So if you remember with contamination, the object or the person that is contaminated becomes radioactive. It's very difficult to get rid of that radioisotope once it's on or in you. Whereas irradiation, as soon as the source is gone, a bit like switching off a light, then there's no radiation around. The equipment is not radioactive. It's just been exposed to radiation passing through it. And that's the end of the video.